Hey guys, welcome back. Hope you guys had a nice break. So we'll just get back to spatial statistics. So we finished last time by talking about spatial correlation functions. And the big takeaway here, there is a lot of spatial correlation functions to be had. They're all going to look something like this. The correlation between observations taken at two locations are going to be a function of interpoint distance. And that function depends on some parameter and the interpoint distance. Here it's e to the power of negative phi times the interpoint distance. The covariance then just multiplies the correlation function. This is our correlation by sigma squared. And that becomes the basis of our models. It becomes the variance covariance matrix specifically, we put into the multivariate normal distribution. And we'll see that later on today. So the phi parameter, it describes how quickly correlation decays with distance. And sometimes this is called the range parameter. But not to be confused with the range, because you can see, for example, with the orange line, when phi is 4, the range is certainly not 4. The range is closer to 1 than it is to 4. So it's important to be very precise when we're talking about the range, the distance where correlation goes to exactly 0, and the range parameter, which is just a parameter inside of our spatial correlation function. Now, our intuition about this range parameter depends on exactly how that correlation function is written. If it's written like this, then as phi becomes larger, so does the correlation. As phi becomes smaller, so does the spatial correlation grows. The green line indicates that when we're out here at a distance of 6, we are still correlated at a clip of, 0.3, whereas the blue line, at a distance of 6, we're no longer correlated. So it's hard to immediately, when you're applying software to a problem, you really have to dig in how they parameterize their correlation functions, and that is really annoying. And we'll see a workaround in a little bit. So I call this the correlation function zoo because it's just a whole lot of different correlation functions. The big ideas to take away is there's not sometimes a whole ton of information to estimate this parameter, because you see I multiplied it by 4 and the data look very similar. The other issue, as we're changing correlation functions, unless data correlation is very strong, we may not have a ton of information to differentiate not only between the values of that phi parameter, but also between different correlation functions. So here is a Gaussian correlation function. Here is an exponential correlation function. If you pay attention to these two panels, you see they look very, very similar. So if the amount of correlation in your data is moderate to weak, you may not be able to distinguish between values of phi, and you may not be able to distinguish easily between different correlation functions. Now, yes, of course, there are people who spend their entire career studying correlation functions. So there is value in understanding their point, which is to introduce how, to impose a systematic way in which correlation decays with distance. But practically speaking, unless you have a strong spatial dependence, there's just not a ton there to differentiate between these parameters. We can have functions with 2 parameters, but my cautionary tales remain. We can have helpful function like, oh, and my, this is great. For some reason, this particular presentation is just causing problems. I think it's just way too many images, and PowerPoint hates me. So that's okay. We like the spherical because 1 over phi, the way it's written here, 1 over phi is actually the range, is actually the range. You see in the blue line, phi is 1, the range is 1. That's the distance where correlation goes to exactly 0. We see here the green line, phi is 0.25, the range is 4. So that might be why we like the spherical correlation function. May turn is popular, also depends on 2 parameters. There are several important special cases, among which when this nu equals 1, we get the exponential back. But I don't want to linger on this topic because, as I mentioned, oftentimes it is not as important which spatial correlation function you pick. It is more important to account for spatial correlation when it's present and pick the right likelihood, pick the right mean function, things like that. There are a few unique spatial correlation functions like this dampened wave. So you see, it is the only one that at least I know of where we can actually have negative correlation for data points that are near to one another. So this is something that is applied when you have some kind of porous media. So think about sound waves in a porous rock, where you have a dense space right next to an empty space. And as you're getting farther and farther apart, you're oscillating between areas of positive correlation and negative correlation, positive correlation and negative correlation. The interpretation of this phi parameter is rough here. There is not really a unique range because even as we get far apart, we're still, getting these areas of negative and positive correlations. Have I ever seen a paper where the dampened sign correlation function was used? The answer is no. Could there not be? Of course there could be. I cannot possibly know every single application. I can see there, specifically in engineering sciences and geological sciences, there being a use for this. If we're testing something like the hardness of the soil, you could be hitting different kinds of soil and oscillating between positive and negative correlations at nearby distances. So nugget only is a limiting, this is a limiting correlation function when the range, not the range parameter, the range goes to 0. So we don't have a ton of spatial dependence. And if we don't have spatial dependence, the correlation does not change with distance. No spatial dependence means correlation constant with distance. Sometimes you will see the word exchangeable used for this kind of correlation function. And I think this is a helpful word because it helps you visualize what exchangeable really means. Exchangeable is another way of saying no spatial dependence. That means that we can rearrange our locations and results stay the same. And I just covered this. It's a limiting case where the range goes to 0, so data that are nearby are essentially independent. And in some cases, you would call this a random intercept model. If you're more familiar with like a hierarchical random intercept model, if there is no spatial correlation between the intercepts, you have a random intercept model. If you do have a spatial correlation between the intercepts, then you're going with a spatial model. How would you compare? Well, first of all, to pick a correlation function, you can find things like AIC, BIC, corrected AIC, and we'll go over that later in the course. But I always advocate for science first. If you're dealing with porous media, then maybe you would consider a dampened wave correlation function. If you're dealing with a typical ecological application, there is no reason to deal with a dampened sign correlation function. So this slide essentially summarizes all of those thoughts. The key here is you have to be careful when you're opening up a new software because in some software, all of those correlations are written in terms of 1 over phi or 1 over rho or rho, and that will of course flip all of your intuition and all of your interpretations. So we go back to this spherical. In some cases, people just, because it's 1 over phi that is equal to the range, they just, instead of phi, they write 1 over phi there. So be careful, whether it's ArcGIS or a new package in R, you have to be sure exactly how their spatial correlation functions are parameterized. Okay, let's move on to the effective range. Because of a variety of these issues, that the range parameter by itself is not interpretable, that we get into trouble using software without understanding exactly how those functions are parameterized. It is helpful often to look for the effective range. And this is, again, not the actual range. The range is where the distance, where correlation goes to exactly 0. The effective range is where the distance where correlation becomes arbitrarily small. And arbitrarily small most often, but not always, means 0.05. Computing this effective range depends entirely on the spatial correlation function that you picked and whether it's parameterized like this or like this. So it almost forces us to understand how these things are parameterized. It just refuses. It just refuses, guys. Computing the effective range forces us to understand which of the two parameterizations is out there. And the effective range, I claim, has a lot more intuitive interpretation. We don't care if the correlation between observations is 0.03. We care around where things stop being strongly correlated. And that, I argue, is more in line with the effective range. So, for example, if you have an exponential correlation function, to find this effective range, you simply take it and you set it equal to your arbitrarily small number. And you see that now I put a little star over the distance because I'm going to solve for h star now. And this becomes the effective range. Sometimes effective range is called the practical range. So the first thing we will do is take a log, natural log of both sides. right, now we're going to multiply both sides by -1. And we're not going to worry about the fact that we've multiplied both sides by -1, because the natural log of a number that is between 0 and 1 is negative. So by multiplying both sides by -1, we actually now ensure that our effective range is positive. Of course, it has to be positive because it's a distance. And we finally now divide both sides by phi to find this solution. So whatever phi you estimate, if this is how the function is parameterized, whatever phi you estimate, you take negative log 0.05, which is approximately 3, right? So it's approximately, give me some space. This is approximately 3 over phi. That's the effective range if our function is parameterized this way. But you can see again, and I keep harping on this because I know there are packages and I know there are software routines that parameterize it this way. Your intuition, your computation will be wrong. Please be sure. When in doubt, solve it yourself. So let's try a different one. Every correlation function will have its own effective range. This is the Gaussian. Well, you guys can kind of guess what's going to happen. We're going to take the log of both sides. We get and multiply both sides by -1. So we get phi h star squared equals negative log 0.05. So I'm going to take the square root of both sides and divide by phi. So my h star is square root of this quantity divided by phi. So this is very, very important, which means that you can't just look at the magnitude of phi and compare it directly between the exponential function, correlation function, and the Gaussian, and the spherical, right? In the spherical, remember, 1 over phi is the range. In short, the best way to compare what different correlation functions tell you about the degree of correlation in your data is to compute the effective range. The way we compute the effective range, you take a function and set it to an arbitrarily small number, usually 0.05, and then solve for h. You can do this programmatically, you can do this manually, or some software will do it for you. But again, be careful with defaults. Okay, estimation. Quick review, I've already done a review this section, so I will just kind of let you guys read through that. Here is our likelihood. It is multivariate normal. X prime beta is our mean that is varying in space. Alpha squared is the partial CIL. Isn't it cool that we can just use these terms without definition because you guys know what the definitions are? And tau squared is the nugget. So let's dive into the multivariate normal more deeply. What we're going to do is we're going to kind of do a maximum likelihood estimation by hand. We're going to use our observed vector of observations, y, our design matrix, which contains all of your covariates, quantitative, categorical, everything, and h, which is your distance matrix. The thing is that I can't do this with pencil and paper. I also wouldn't want to do this pencil and paper because I have a parameter inside of I have a parameter inside of my variance covariance matrix that controls how quickly the correlation decays with distance. So I will do this numerically by using Optim, and then we're going to show that we match the results that are produced by a variety of different software packages. That way we can understand better how the software does it. And we get to trust the software. We get to trust our own intuition about this stuff. Here is the likelihood. You see that it depends on is our variance covariance matrix. This is our variance covariance matrix. Notice our variance covariance matrix has the partial sill, the nugget, and the range parameter in there. Partial sill, nugget, range parameter in there. H is known because H is the distance matrix. Then we have this y minus x prime beta. These are basically the residuals. These are the residuals. So, take the next step. We have this wonderful thing called generalized least squares. So you guys might recall the least squares estimator says that our betas from regression class, our betas from OLS, not GLS, from OLS, we say, okay, beta hats are x prime x inverse x prime y. But this says that our data are independent. Well, we're in spatial statistics. Our data are not independent. So OLS gets generalized to GLS, or generalized least squares. And what we, instead of the identity matrix right there, identity matrix, of course, has zeros on the off diagonal, we put in our sigma inverses. So the generalized least squared estimator that allows for spatial correlation looks like this. It's x prime x, and including the sigma inverse, x prime sigma inverse y. Again, if our data are independent, our sigma inverse becomes the identity matrix, and our GLS goes to OLS. So if we come back here, we come back here. We have all kinds of parameters on the screen now, but once we find our sigma inverse, we just plug it in to the betas. And we only need to maximize the entire log likelihood over the parameters inside of our sigma. Once we find sigma, we simply use the GLS equation to find our betas. And those are no longer, those are basically linear combinations of data and known quantities and not standalone parameters. And this is the slide that makes this clear, hopefully more clear in a lot more Greek letters. Here, I'm writing betas as being explicitly dependent on our estimate of the variance covariance matrix. And then, if that's the case, then the only thing we have to do is estimate the parameters inside the variance covariance matrix, and then plug them into beta. So this reduces from having a oh, I don't know, p-dimensional maximization task, right? This usually you have a lot of different betas in a regression model, to a two-dimensional maximization task. And then you use your estimated variance covariance matrix and simply plug it in to find your betas. That was a lot of talking and arm waving. Let's kind of dive a little bit into the data. So for the data, I'll be playing around with the Colorado temperatures example, which is something that you guys did for your homework 1. I've got R here. One thing that I'm doing is I am leaving my geometry as in terms of latitudes and longitudes. So my distances are going to be in decimal degrees. We've had plenty of practice reprojecting those to meters. Here, I just chose not to. Feel free to redo the exercise with a reprojection. You can even drop a note about how that changes things. Let me go through the maximum likelihood portion first, and then I would like to come back and show you this variogram fitting exercise and really how not particularly useful it is. Okay, MLE by hand. So first things first, I can make a plot of my January temperatures. I have cool colors and warm colors representing cold temperatures and warm temperatures. There's clearly spatial dependence here, but there's probably a need to account for elevation because, not surprisingly, elevation increases as we go from the east to the west in the state. Here is what my residual variogram looks like, and it includes elevation. And this looks like, oh, I don't know, maybe the sill is somewhere right over there. The nugget is pretty close to 0. The range is, oh, probably around 3. And as a reminder, I'm keeping the distance in degrees, just to show you guys something different, in decimal degrees. So I did not reproject from latitude and longitude to UTM meters for this exercise. Remember that what my MLE by hand requires, I need the distance matrix that will give me interpoint distances to put in to my correlation function. I need the design matrix because that has all of my quantitative covariates, in this case just one, elevation, but also the intercept as well. And finally, I need my outcome vector. In this case, this is just the average January temperatures. Okay. You guys have seen this code before. I am pulling off the coordinates of my spatial data set. I'm finding the distance among those coordinates, and I'm making it a matrix. And I can then plot the matrix. Of course, it has zeros on the diagonal. And sometimes it's useful to note just how far apart our data can be. 8 decimal degrees is the size, the largest observed distance in decimal degrees. Here is my design matrix. It has a column of 1s for the intercept. And here is my scaled elevation. By scaled elevation, I'm making a z-score for elevation, which means it's elevation minus the average elevation divided by the standard deviation of elevation. It's good for computational purposes to do this. And finally, here is my observed data as a single column matrix. I need to do this as a matrix to make the matrix algebra work, because I'll be using R to do some matrix algebra, right? I need matrix algebra for this GLS equation to work. All right, matrix algebra happens here, right? So for this multiplication specifically to work right there, I need to cast Y as a single column matrix. Okay, let me flip to R. Here are all of my ingredients. And I will have to pull in this library called MVT norm that has the multivariate normal density as a part of it. And here is my multivariate normal log likelihood function. I have to give it my two parameters. This is a vector of parameters. And these three things are my three ingredients that are unknown. There's nothing to be estimated there. Whoops, this is not entirely correct. So here I am simply for notational purposes, taking theta 1 to be alpha squared, which is the partial self, and phi as the range parameter. Not the range, not the effective range, the range parameter. Right over here on line 70, I am building my variance covariance matrix. And this, of course, has the form that we saw earlier in the lecture. Alpha squared times a function of my distance matrix. For this exercise, I'm assuming that my nugget is 0. I'm assuming that my nugget is 0 just to make it easier on us to kind of conceptualize this maximum likelihood by hand. And also, you know, I think it's okay for now to assume that the nugget is 0. The nugget really could be 0. So that's not a particularly crazy assumption to me. In general, don't assume the nugget is 0. But for this particular exercise, that's okay. On line 75, I'm applying the GLS equation. So here is my x prime x inverse bit, right? The solve function in R takes the inverse. Here's x prime, here's x, and here's sigma inverse in between. I could have just done it in one line, but I wanted to make the code as readable as possible. X prime, sigma inverse, y. Again, to make this work, you need to make sure that things line up in terms of their matrix algebra. Sigma inverse is going to be n by n. That means your y has to be n rows by 1 column. That's the way to make this multiplication work. So here are your two parameters to be estimated. Here you make your betas because your multivariate normal needs a mean and a variance covariance. So here is your variance covariance. Here is you're going to make the mean using these betas. And here you will evaluate the multivariate normal log likelihood. It's a log likelihood because log is true. Here is your variance covariance matrix. Here is your mean vector. X is n by p. Beta is p by 1. That means that this mean vector is going to be n by 1. The sigma is going to be n by n. This will evaluate to a scalar. This will evaluate to a single number. And then we have a trick. To use the optim function, what optim does is it iterates over different values of your theta vector to make your last line, whatever you return, as small as possible. By default, it makes it as small as possible. We don't have a minimum likelihood, we have a maximum likelihood. So the trick is to return the negative log likelihood, because making the negative log likelihood as small as possible is the same as making the log likelihood as large as possible. So this is just because, only because optim minimizes by default. and we need to maximize the log likelihood. So I just wrote a little function, a little ditty here. Here's my function. So when you write your own function, it's helpful to test it. For example, here are two values of my parameter. Here's alpha squared. Here is my range parameter phi, given the distance matrix, the design matrix, and the vector of observations. And I want to make sure this evaluates to a number, a single number. So what Optim's going to do is it's going to change these values around until this number is at its maximum. It's helpful to make sure this works for a pretty large range. So here I just multiplied this by 100, this by about 300, and it still produces a number. All right, we're ready to let this baby go. I have a small typo here because theta squared is sigma, theta is sigma squared, and theta 2 is phi. And we are assuming again the nugget is 0. So we need to give it starting values. Sorry about the little typos, guys. Sorry about the little typos, but keeps you on your toes and keeps me on my toes. We need to now give starting values for my partial cell and my range parameter, assuming the nugget is 0. I'll go back here. Assuming the nugget is 0, it looks like my alpha squared is about equal to 0.06. And my range, not range parameter, my range is about, I don't know, somewhere in between 2.5 and 3. So I clearly thought that my range was 2.5, because if I am imposing the exponential correlation function, then I need to provide a reasonable value for phi. That means I need to, if I think that my effective range is somewhere between 2 and 3, then a reasonable initial value for phi is going to be 2.5 over negative log 0.05, right? So I thought that my effective range was somewhere between 2 and 3, call it 2.5, and using that, this is how I specified this starting value. Now, of course, I could have just picked another number like 2 or 3 or 1, but the better the starting values you pick, especially for this manual MLE, the better our result. All right, let's make it run. It runs very quickly. Here is our output. One thing to look at is convergence. For those who have never used Optim before, a convergence value of 0 means everything has found its peak. It has found its maximum. So anything other than 0 indicates that it has run out of iterations, an error has occurred. It needed to perform 47 iterations to find its maximum. Here is the negative maximum likelihood value. And here are our estimates. So 0.063 is our estimate for alpha squared, which is the partial CIL, but we're assuming the nugget is 0. So that's also our CIL. And here is our estimate for phi, the range parameter. So this was our log likelihood by hand. I can also build my beta parameters. Remember again, I'm going to apply the GLS equation here. Looking for the slide. There we go. I now am going to apply the GLS equation. I've just computed alpha squared equals to 0.06. I computed phi to be 0.94, and I'm assuming that tau squared is equal to 0. So I can just build my betas back up. And here they are. Not surprising, the coefficient of elevation, of scaled elevation, is a negative number. Because as we increase elevation, temperature tends to decrease. The last thing we do today, and I'll talk about the other stuff next time. This has been kind of a long and detailed lecture to date. Let's verify using a bona fide R package. So this bona fide R package is going to be called GeoR, and it's a pretty powerful one. Annoyingly, it has its own data format, which is the stuff you run into if you do spatial analysis in R. Everybody has their own data format. So notice that I have to sort of build my, rebuild my data frame. So I'm grabbing the coordinates out of my spatial object, and I'm rebuilding the data frame. Now I'm putting the x's are longitudes and latitudes next to elevation and average temperature in January. If you wanted to play around with this and fit these models for the other months, feel free. It should all work for you. So we are going to have to now put in this GeoR data format. So here is the data frame. And now we give it the column numbers that correspond to our coordinates, the column number that corresponds to the data, the January average temperatures, and the column number that corresponds to the covariate. And finally, we estimate the model. So here is the geodata object. Here are our initial guesses. I could set this back down to 0.06, which would match the initial guess that we put into the MLE equation. We can set this to be the same as well. Log, negative log 0.05. By the way, our initial guess for phi is 0.83 because negative log 0.05 is approximately 0.083, excuse me. I am setting nugget equal to 0, and for this exercise, I'm fixing the nugget at 0. I'm specifying the trend as being defined by centered and scale elevation. I'm specifying the spatial covariance as exponential, and I'm performing maximum likelihood. All right, all together now, let's make sure that our hand-rolled maximum likelihood estimation produced something close to the right result. All right, right over there, here is my partial cell. One good thing about GeoR, the output is long, but it's very clear exactly what is being estimated. Estimation method, maximum likelihood. Parameters of the mean component. Beta 0, the intercept, was 17.09. We estimated 17.09. Cool. Beta 1, which is the coefficient of centered and scaled elevation, 0.2284. We estimated 0.2284. Let's just make sure that to be the case. Looks like that time was off by a little bit. Let's, I apologize for these little typos. I was trying a different way of solving this, and I did not fix it to go back. All right. This now matches exactly what we found. So we simply plug in the MLE estimate of alpha squared. We plug in the MLE estimate for phi. We get these as our estimates. And if we now check with the bona fide package, we should be now matching pretty much exactly. Here is minus 0.2284, 0.1709. Here is my partial sill estimate, 0.06. If we come up here, 0.063, 0.0632. The fee is just a little bit off, but this is still quite close. Very, very close. Anisotropy parameters, for now, we're not touching those, but in the future we will. Our nugget parameter is fixed at 0. The GOR gives you a possible Box-Cox transformation. We're not doing that right now. And importantly, it's one of the few packages I know that gives you the effective or practical range as well as the range parameter. So this is our effective range for the exponential correlation function, which was negative log 0.05 over phi. So this is our distance at which the effective, the correlation function becomes arbitrarily small. The other important bit here, here is our log likelihood estimate, 13.42. We found the negative log likelihood of negative 13.42. So these are, of course, matching up, only we have the negative of that, and he has the positive of that. So this is essentially what is happening underneath the hood of our R package. I'll kill this for today. I apologize for the little typos. I was just playing around to see if there was another way of doing it. Next time, I will finish up this particular R code, so specifically the other ways of estimating this model, and I will also discuss the pitfalls of fitting variogram models. So thank you guys so much for your attention. I hope you're well. Stay safe out there. I'll see you later.